Welcome everyone. This talk is my interpretation of the different flood risks that impact that part of the Lee Valley that is occupied by Cork. The fact that the medieval city was reclaimed from an estuary has been a key factor in its subsequent development. However, it is only relatively recently that geologists and engineers have begun to understand the ground and groundwater conditions that underlie Cork. I'd like to acknowledge funding from the Heritage Council in the early stages of my research. Support also came from the Department of Archaeology, UCC. Bert Dufour, a graphic designer, helped me to draw up some of the maps and sections. Most people who live or work in the city are familiar with the different types of flooding that impact it. There are three types: tidal surges, river floods, and groundwater. The last of these is perhaps the least well understood because its origins are below street level. But Cork is not unique in being subject to flooding from both the land and the sea, because there are many cities and towns in the world that have been located on estuaries. However, because Cork was built on the outer reaches of the Lee estuary, or further out to sea, so to speak, its conversion to an urban landscape has been particularly difficult. For example, the city is extremely vulnerable to tidal surges, and its water table is relatively high. An additional problem is that the upstream catchment of the River Lee above Cork covers a relatively large area. This slide shows appropriate investigations in order of decreasing importance. In an urban context, where the landscape and the geography has been obscured, the subsurface environment is as important as the visible landscape, and therefore methods of study are different from those that might be relevant in a rural context, where landscape features such as rivers are visible. Thus, remote sensing techniques such as aerial photography, satellite imagery, and geophysics are almost redundant. Instead, the useful techniques in Cork include historical maps and documents, engineering boreholes, urban archaeology, and so on. There has been a major increase in the knowledge of Cork's underlying ground and groundwater conditions in the last 25 years. The following slides provide an introduction to some of the new methods. Historical maps. Good quality information is available from a large number of historical maps that cover Cork. However, the surviving maps date from only the second half of the 16th century, by which time the centre of Cork had already been reclaimed. Nonetheless, it's possible to reconstruct the course of the estuarine channels that occupied the Lee floodplain before the city was built. This was achieved by plotting the channels onto a large-scale Ordnance Survey base map. In this slide, I'm showing some of the more important maps. In general, they evolved from an artist's bird's-eye views of the medieval city, for instance in 1587, to properly surveyed maps. The first of the surveyed maps was the military map drawn up by the Navy engineer Thomas Phillips in 1685, shown bottom right. Much useful information was also found on Ordnance Survey maps surveyed in the 19th century. Abundant evidence from engineering boreholes completed between 1955 and 2012 is available for the centre of the city. This plan shows 240 boreholes from 114 site investigations. Nearly all the investigations were based on what are called cable tool percussion boreholes. These provide high quality information based on sampling and strength testing. I was involved in this kind of work and therefore was able to interpret the driller's records in terms of a basic stratigraphy. This slide shows the typical stratigraphy in the boreholes. In this example, there are some 3 meters of filling, including granular and cohesive soil types, overlying about 1 meter thickness of estuarine mud, shown here in green, which in turn overlies saturated sand and gravel of fluvial origin, showing in orange. On the right of the figure, I've also illustrated the typical tidal range in the city. In many of the boreholes, water is struck both in the filling and in the underlying sand and gravel aquifer. If measurement of subsequent water levels is taken over a long enough period, then a close relationship with the tide cycle is often found. A review of reports covering some 16 archaeological excavations was also completed. All these selected excavations intersect both man-made and natural strata. The detailed nature of an archaeological survey means that the sediment sequences can be viewed in great clarity, leading to accurate descriptions of stratigraphy and sedimentology. This image, taken in 1997, shows one of the archaeological digs where dewatering was first used, so allowing a much more comprehensive evaluation of Cork's development. Formerly, there had been a big problem with the depth of investigation, but this difficulty was overcome by using pumping wells that reduced the level of the water table, allowing high-quality data to be collected from depth. In this case, observations of the fresh cuttings enabled a distinction between the mud that had been brought to raise ground levels in the medieval period and the underlying naturally formed estuarine mud. The deepest layer was the water-bearing gravel, which is of fluvial origin. Comprehensive dating of timbers and organic material was also possible. More high-quality information is available in basement excavations that have been completed around the city. Many of these exceed 5 meters in depth. The example in this image on the left is the basement of the shopping centre on the east side of Cornmarket Street, which was opened in 2006. In the foreground, it is possible to distinguish a river bar that is laterally adjacent to dark grey estuarine mud. The thickness of the mud increases towards the east in the direction of the multi-storey car park in the background. On the right is a picture of one of the bored pumping wells that enabled major dewatering of the underlying gravels. Certainly a clear view of the geology. I hope that gives some idea of the methods that lie behind this review. Now we move on to the different flood types and the risks that are associated with them. This slide illustrates a typical tidal surge. It occurred on the 20th of October last year at 8:30. Tidal surges mark a particular combination of weather and tide. In this case, a low-pressure system moved across Ireland from the southwest at the same time as the highest part of the tide cycle. The low atmospheric pressure, southerly gales, and spring tide all added up to an exceptionally high sea level. As a result, an increased volume of seawater entered the mouth of Cork Harbour and surged into the Lee estuary, causing flooding. Similar events are frequent. Therefore, tidal surges may be considered as high risk and high impact. These two pictures were taken by my colleague John Moorhead. They demonstrate contemporary events that occurred just before dawn on 16th of December last, when a minor tidal surge arrived in the South Channel. At about the same time as the tide overtopped the quay at Morrison's Island, water emerged from the drains along Phoenix Street and Crane Lane, shown in the right-hand photograph. Therefore, some of the flooding took place away from the North and South Channels, of which more later. As Dr. Michael Creed, the former head of engineering at UCC, has pointed out, these are the typical initial signs of a tidal surge in the city centre. The other common surface water flooding are river floods. At Cork, there are several risk factors associated with them, some of which are listed here. Obviously, the primary risk is overtopping of the north and south channels. In addition, it's been established by the OPW that the Bride and Shornoch tributaries also have a significant input into flooding in the city. Then, according to Kieran Hickey, who is head of geography in UCC, the impact of water releases at Inniscarra Dam have contributed to several of Cork's recent floods, including the events in 1960, 64, 88, and most notably, of course, the disastrous flood of November 2009. Another risk factor are the overflows caused by culvert screens that have become blocked by refuse material. This has been a common factor in river flooding in other towns and cities of Ireland, and as Chris Moody has clearly shown, has damaged Blackpool on more than one occasion. It is outside the scope of this talk to attempt a detailed review of all the risk factors associated with river floods. However, there is one factor that has not been adequately assessed that I would like to talk more about. There are a number of historical channels that run under the city streets. These waterways have been gradually covered over but still carry water through the urban landscape. My studies show that prior to the medieval land claim, when the estuary was in its virgin state, there were an order of 10 different channels draining the Lee floodplain. These were orientated broadly west to east, except near the open channel of the harbour, where they were deflected towards the northeast. The numerous marsh islands defined by these tidal channels range from deep water mudflats to reed beds, which we know from archaeology were located around the margins of the floodplain. The reed beds would have been above mean sea level, while the mudflats would have been submerged for most of the tide cycle. Undoubtedly a difficult landscape to convert into a city. By the 1750s, the land claim had proceeded, so that about 3/4 of the marshes were covered. Importantly, we can see here that there were a number of cross-cutting canals, which date back to the medieval period. Some of these were widened to take ships rather than smaller boats. By the mid-18th century, canals along Patrick Street and South Mall had also been excavated, while at the same time some of the natural waterways in the smaller canals had begun to be culverted and backfilled. Moving on to the modern city shown in this slide, we can see that only 2 major channels survive, and that they flow along the northern and southern edges of the estuary, leaving the centre of the city completely built up. So there are considerable volumes of water still flowing under the urban landscape. The next 2 slides are a brief tour along Cork's former canals. The first image, top left, shows the culvert that bridges over the former Eastern Canal at Grand Parade. It was uncovered during work on the Cork main drainage scheme. Note how water moves sluggishly through an old brick and stone arched culvert. Note also how the water is close to street level. The image at the bottom left shows the impact of the 2014 tidal surge, which occurred in the late evening in the same area. This time the view of Grand Parade is taken from O'Sullivan's Quay, where archaeologists believe there was a medieval harbour. A northern extension of the Eastern Canal ran under Cornmarket Street, which many know as the Coal Quay, shown in the third photograph. Note again the significant width of the street, which was a place where ships once berthed. This is an example of a later canal which now runs under the South Mall in Cork. It was first shown on the military map by Thomas Phillips, mentioned earlier. This particular canal seems to have been formed by straightening a pre-existing estuarine channel. It was essentially a merchant's canal and has a number of features that are similar to an old Dutch type of canal known as a gracht. The boathouses that join the canal are still visible in the streetscape. We now move to groundwater flooding, which is the least researched flood type. This is despite the fact that there is a widespread local knowledge of water rising from the ground both during spring tides and during storm surges. The picture shows a temporary trench excavated in Princes Street last November. The trench was taken down to a depth of about 0.8 metres below street level and happened to be open during the highest part of the tide cycle. John Moorhead, using a video camera, was on the spot and showed very clearly that the rise and fall of water in the trench matched the tide cycle in the South Channel with very little time lag. Significantly, the water table rose to within a foot of the street level. Of course, this is not a new phenomenon. As stated earlier, a tidally influenced water table has already been identified in many boreholes. I decided to carry out a preliminary survey of historical cases by interviewing shopkeepers and property owners. In a short time, I identified about 17 locations with groundwater flooding, as shown on this figure. Of course, the data is only preliminary and there must be many more locations. However, the statements that I heard indicate a widespread history of tidally forced water issuing from drains, structural cracks in pavements and walls, and shallow excavations. I think that this quotation obtained from Twitter gives a very good idea of the nature of groundwater flooding in the centre of Cork. Finbar Cotter identifies a number of features which have been repeated by other people that I interviewed. He says, "On many occasions over the years, we were flooded in our back doors by rising water levels through shores, manhole covers, drains. This after making every effort in sandbagging front and back doors. Not a hope could we prevent water rising inside our premises, as the water found gaps in our floor plates, cracks in walls, and so on." If we zoom in to just one part of the city centre, we can see a cluster of 9 locations between South Mall and St. Patrick's Street. For the base map, I've used a historical OS map surveyed in 1899 because it shows the older footprint of the terrace buildings. Based on interviews, it's possible to draw some preliminary conclusions. Firstly, a fluctuating water table is visible in shallow excavations, as shown earlier. Secondly, some groundwater rises via earthenware drains into backyards. And thirdly, the Cork main drainage scheme has helped with the drainage of groundwater at some locations. That's since about 2003. The reports of water entering backyards through old drains is not surprising, given that these forgotten nooks and crannies have not been modified much since the 18th and 19th centuries and are consequently still low-lying. It seemed a good idea to plot the groundwater locations on a map that showed the underlying waterways of Cork, to see if there was any relationship. I chose the 1750s plan because it includes both natural channels and later canals. There does seem to be some correspondence shown on this slide, but on the whole the match with the underlying waterways is poor. Therefore, while some of the groundwater may derive from historical channels, there must be more to the story. This plan shows the thickness of estuarine mud in the city centre based on historical boreholes. Notice how there are several thick developments of mud, including along what was probably the main central channel in the estuary, which today extends between Triskel and Oliver Plunkett Street. At the same time, mud is almost absent in other areas, such as north of Patrick Street, for example at Paul Street, Cole Quay, and Lavitz Quay. How does this variability compare with those locations with tidally forced groundwater? The answer is very well. One can immediately see that there is a strong correspondence between groundwater locations and the underlying geology. I would interpret this as strong evidence of perched aquifers. By grouping these locations with by grouping those locations with tidally forced groundwater, the close relationship is even more clear. Thus, during extreme high tides and tide surges, groundwater is being held up by the underlying estuarine mud so that it forms aquifers of local extent in the man-made filling above. There are a number of sources which probably contribute to these perched aquifers, which would be both natural and artificial sources, of which more later. First, we can see further evidence of perched water when we look back at old pictures of temporary excavations in the city. The excavation here was located at the east end of Castle Street during the early days of this Cork main drainage scheme. Owing to its location in the medieval part of Cork, it was monitored by archaeologist Catherine Power. Note how water is sitting on cohesive material at the base of the trench, perhaps having percolated through the gravelly layers above, or it may simply have leaked from the old sewer. In any case, water is ponding underground. No wonder that some of those whom I interviewed told me that groundwater flooding is worse when there's been heavy rainfall. I also put in this image of the archaeological excavation on South Main Street, completed 2005. It shows how the estuarine mud prevents discharge of the surface water to lower levels. Extensive ponding is obvious. How difficult it must have been for the medieval slaves to construct the substantial oak fence that is shown, waiting for each low tide, and then to bring clay from elsewhere and dump it on the low-lying mudflats. When we assemble all the risk factors, we can see that the different elements of groundwater flooding are not straightforward. I will consider that the risks include perched water as just discussed, groundwater in the underlying fluvial gravels, and some of the water in the historical channels. In other cities, engineers have found that leaking water mains contribute significantly to underlying aquifers, as do leaking drains. There is also evidence that large volumes of water can enter through pavement cracks directly into the underlying sediments. A complicated picture, I think you will agree, and the summary must be that the groundwater flood risk has not been properly assessed in Cork. The next question must be, is it possible to assess the flood risks objectively? This slide shows a stylized section through the Lee floodplain. In it, I have tried to show the different hydrogeological layers, flood types, and flood risks, all in one figure. In brief, the youngest strata may be summarized as variable filling of medieval to modern date. Within this filling, there is a complex network of drains and water services. Historical channels are shown extending into the underlying estuarine mud, which is not continuous across the valley. The lowest sediments comprise saturated sand and gravel. Then there are two bedrock types which underlie the northern and southern ridges of Cork. To the north there is sandstone and siltstone bedrock, and to the south limestone, which, being a major aquifer, is probably recharging the adjacent gravel. The different flood risks shown include river floods and tidal surges in the north and south channels, and perched groundwater above the estuarine mud. Note how the perched groundwater may be actually discharging into the underlying fluvial gravel during the low part of the tide cycle. It's useful to present these flood risks in terms of mathematical parameters. If we take just one area, say the east and downstream part of the city, we obtain no fewer than 9 flood risks. I have presented them in this preliminary equation as Ts, tidal surge, T, the tide cycle at springs, F1 and 2, the river flow in north and south channels, FH, the flow in historical culverted channels, P, the perched aquifers in gravelly filling, G, the partially confined gravel aquifer at depth, L, the limestone aquifer, U1 and 2, leaking water mains and drains, and U, urban runoff through city pavements. The important point is that many of these risks are uncertain and have not or cannot be quantified. All this adds up to the conclusion that computer models of Cork City's hydrogeology cannot be considered to be representative. Unfortunately, such modelling has formed one of the foundation stones for the OPW decision to use direct defences at Cork. So in summary, we can conclude that Cork City is characterised by combined surface water and groundwater flooding, and that sustainable options must take this fact into account. Here are some conclusions. The graphic to the right is a drawing by Arup Consulting Engineers and shows the proposed sheet pile solution at the Tyndall National Institute. Note how the piled wall extends to several meters depth, which the exact amount of which has not yet been specified in the design. Note also how backfill will cover the existing stone quay. The same solution is proposed for many other stretches of quays in Cork. I believe that the new measures will artificially separate surface water and groundwater, despite the lack of understanding of their interconnected nature and the risks associated with them. I also think that Cork is one of those places where hard engineering solutions are not feasible. In the Netherlands, it has become not the norm to avoid flood relief schemes that exceed the limit of engineering capability and instead use a toolbox of smaller scale and softer engineering methods. Instead, I believe the solutions should be located away from the city, both up and downstream from the city, a view that has been articulated by other experts and organisations. The recommendation to mitigate flood risk by introducing changes to operational procedures at the dams has already been adopted by the OPW. Another sustainable option advanced by Philip O'Kane is to enlarge upstream storage and, as part of this approach, modify the capacity of the Inishkara and Carrigadrohid dams. The third option is to install a tidal surge barrier at an appropriate location and to apply a sophisticated forecasting system to work in tandem with the tidal surge barrier. Finally, I'd like to make the point that there is an overemphasis on the 2009 river flood in the proposed Lower Lee flood relief scheme design, particularly when one considers that last year the Supreme Court found that the ESP was negligent in relation to the damage caused by that flood, with UCC guilty of contributory negligence. Therefore, the 2009 flood should be considered as a flood event that was not representative of the typical pattern of flooding in Cork. I will leave my review there. Thank you.